Okay, so welcome to this next video in the playlist on vector spaces. In this video what we're going to talk about is subspaces of vector spaces. Okay, right. So initially what we're going to do is just remind ourselves of the definition of a vector space over a field F. Then what we're going to do is have a look at the definition of a subspace. Then what I will do is show you the three criteria for being a subspace, and then what our job will be is trying to understand why these three criteria are enough. Okay, so why they do the job of making sure that something is actually a subspace, and then finally what we'll end up with is discussing examples of subspaces. Okay, right. So firstly, let me just remind you of the definition of a vector space over the field capital F. So I'm going to remind you of what it means for V to be a vector space over some field which we'll call capital F. Okay, so a vector space then is a type of number system, okay, and at its foundation what it is just a set of symbols which we call vectors. Okay, so here is V, and fundamentally it is just a set of symbols which I'll draw here. So here is the set of symbols denoted here. Okay, and I'll colour this in red here. Okay, and then on top of this set of symbols what we're going to do is define two composition laws. We're going to define an addition composition law, which will tell us how to add any two vectors together in the vector space, and we're going to define a scalar multiplication composition law, which will tell us what any element of the field multiplied by any vector in the vector space is actually going to equal. Okay, so I'll draw these out here. So here, this can represent our addition composition law, and what we will have is all elements of the vector space given a column in this composition table, and we'll have all elements of the vector space given a row in this composition table. Okay, and then what we'll do is we'll go through, and for every possible combination of two elements from the vector space being added together, we'll go through and define what the answer is actually going to be equal to, and of course all of the answers will be back within the vector space capital V here. Okay, now under addition, the vector space forms an abelian group, so this addition composition table here must obey the axioms of an abelian group, a commutative group. Okay, right, so that's the addition composition law. Now the second composition law is called scalar multiplication, and this is an odd one because this isn't elements of the vector space being multiplied by elements of the vector space. Instead it's elements of the field being multiplied by elements of the vector space. Okay, so here comes our second composition table here, okay, which is called scalar multiplication, given the multiplication symbol here, and I'll just colour in our scalar multiplication table in turquoise here. Okay, and this time what we're going to do is put all of the elements of the field, capital F, down here. So we're going to give all of the elements of the field rows in this scalar multiplication composition table here. And then we're going to put all of the elements of the vector space up here, so they'll all have columns. And what we'll go through and do is define all of the entries here, which will be what any element of the field multiplied by any vector in the vector space is actually going to be equal to, and all of the answers will be back within the vector space. Okay, indeed that's one of the first axioms that this scalar multiplication table must obey. Okay, so I'll now just list out the four axioms that the scalar multiplication law must obey in a vector space. Okay, so axiom number one, and I think I'll actually put it underneath here. Axiom number one that scalar multiplication must obey is closure, and what this says is that you pick any element of the field, so for all little c is an element of the field capital F, and you pick any vector from the vector space, and for all little v is an element of capital V, when you scalar multiply the vector v by this element of the field, little c, the answer to that must be back within the vector space capital V. Okay, so this literally just says all of the answers in this scalar multiplication composition table here must be within the vector space. Okay, you can't have them being outside of this set here. Okay, so that's closure. Axiom number two then that the scalar multiplication composition table must obey is associativity. Okay, and this says if you pick any two elements of the field, so I have C1 and C2, which are two elements of the field, and you pick any vector from the vector space, any little v is an element of the vector space capital V, it needs to be the case that scalar multiplication associates with multiplication in the field. So if you consider what is C1 times C2 times V, so this means firstly scalar multiply the vector V by C2, then you'll get another answer which is a vector, and then scalar multiply that vector by C1. The answer must be the same as if you firstly multiply C1 and C2 together in the field multiplication law, and then scalar multiply that answer, use that answer to scalar multiply the vector V. Okay, so these two different ways of doing it must give the exact same answer. There's only one answer to what a vector scalar multiplied by two elements of the field is actually equal to. It doesn't matter where you put the brackets. So that's associativity. Okay, axiom number 3 then that scalar multiplication must obey concerns the multiplicative identity from the field. Okay, so the multiplicative identity in a field is always called 1. So 1 times any vector in the vector space must equal that same vector back again. Again, a very intuitive law, and this must be true for all little v is an element of the vector space. Okay, so that's axiom number 3, so that tells us about the row in the scalar multiplication table relating to this element 1 in the field. Okay, so if this is the row dedicated to the element 1 from the field, then this row is just going to be an exact replica of this row up here. So where we've got this row of titles for all of the columns where all of these are elements of the vector space, we're going to have a bunch of vectors in a certain order here, and we're going to have them appearing in the exact same order in this row below, basically. Okay, and that's what axiom number 3 here says. And then finally, axiom number 4. Axiom number 4 can be divided into two parts. These are the two distributive laws that scalar multiplication must obey. So part 1 of distributivity says that if you pick any element of the field, so we'll have any little c which is an element of the field, and any two vectors, so I'll just put for all v and v bar, which are elements of the vector space, so you pick any two vectors v and v bar, and I'm sorry about the mess there, okay, it must be the case that if you consider what is c times v plus v bar, okay, and this means add these two vectors together in the vector addition law, then multiply it by this element of the field c, okay, this must be the same as if you firstly scalar multiply each of the vectors by c and then add them together in the addition law. So scalar multiplication must distribute over addition in the vector space. Okay, so that's part 1 of distributivity. Part 2 of distributivity says scalar multiplication must distribute over addition in the field. Okay, so it says that for all C1 and C2 that you pick from the field, and for all vectors little v that you can pick from the vector space, it must be the case that if you want to work out what C1 plus C2 times v is equal to, and this means take C1 and C2, which are both elements of the field, add them together in the field addition law, and then take that answer and multiply that by the vector v using scalar multiplication, this must be the same as if you firstly scalar multiply v by c1 and scalar multiply v by c2, and then add the two of them together in the vector addition law. Okay, so this is, you know, a nice interplay between the field algebra and the vector space, so they're very, very much so linked, basically, when you have a vector space over the field f. Okay, so that's part 2 of distributivity, and that says that scalar multiplication must distribute over addition of elements in the field. Okay, right, so those are the axioms then that a vector space must obey. Okay, so let's now turn our attention to what a subspace is. Okay, so a subspace, just like it has the same relation to a vector space as a subgroup has to a group. Okay, so let's draw a picture for this. So let's now say that this box here is a picture of all of the vectors of our vector space. So it's just another way of drawing this set here. So this is the set of vectors that is going to form our vector space, and it has these two composition laws defined in it. Okay, so a subspace is going to be a subset of the set that underlies the vector space. So to draw it on here, let's say this is our subset here, and we'll call this subspace W. Well, it's not a subspace yet, at the moment it's just a subset, but it's a subspace to be. Okay, so it starts its life off as just being a subset of the vector space capital V. So first thing I'll do is colour it in here. So we'll have it represented in green here. Okay, now you're probably guessing that there's going to be something now to do with it being a vector space with the inherited composition laws on, and that's exactly what this is actually going to be. So basically it's a subset of all the vectors in the vector space capital V, which is very special because if you put the inherited composition laws on this subset, okay, so you put an addition law and a scalar multiplication law on this subset, and those addition and scalar multiplication composition laws, they are going to come from the addition and scalar multiplication laws on the larger vector space. Okay, so they're going to be called the inherited composition laws. If you put those inherited composition laws on the subset W, it is going to be a vector space in its own right, i.e. it's going to be a set with an addition law that is an abelian group and a scalar multiplication law that is going to obey all of the axioms of a scalar multiplication law. Okay, so a subspace then is a subset of the vector space which, with the inherited composition laws of addition and scalar multiplication on it, actually is a vector space. Okay, so let's just go through what is meant by these inherited composition laws. Okay, so if we have a subset W of the vector space capital V, we can define very easily an addition law and a scalar multiplication law with the elements of the field capital F on this subset. Okay, so let me show you how you can do that. So let's start with addition firstly. Okay, so we're going to create an addition law for our subset W here. Okay, so what we'll have is all of the elements of the subset W given a column in this composition table, and all of the elements of the subset W given a row in this composition table. So I'll just colour them in green once again. Okay, like so. And the way now that we're going to define any two vectors from the subset W being added together is just using what they would be if we were working in the larger vector space. So if I have, for instance, some vector little w plus some other vector w bar, so these are two vectors from our subset W here, and I want to know what am I going to define W plus W bar, and I'll actually mark this on my composition table here. Okay, so we'll take the row corresponding to W and we'll take the column corresponding to W bar here. So W plus W bar will be the entry here in our addition composition table. How am I going to define this? Well, these are both vectors from the larger vector space capital V, because W is a subset of capital V. Okay, so I can add these two together in the larger vector space capital V. I can go to this addition law over here, which is on the entire set capital V, and I can say, okay, W is an element in here, W bar is an element in here. Let me just take the entry which is W plus W bar over here, and now I'll put that straight in as my answer here. So really all I'm doing is restricting the larger composition table for all of the elements of V for addition down to just being the elements of W added to the elements of W. Okay, so I'm restricting it down just to the elements of the subset capital W. Okay, so that's the inherited addition law. Okay, and we'll also have an inherited scalar multiplication law, so let me now put the inherited scalar multiplication law here, and similarly what we're going to be doing is just restricting the scalar multiplication law on the larger vector space capital V down to this subset capital W. Okay, so we'll still have all of the elements of the field over here. All of the elements of the field will be given a row in this scalar multiplication composition table. Okay, so I'll colour them all in purple here. But now we're not going to have all of the vectors of the vector space capital V up here, we're just going to have the vectors that are in this subset capital W up here. So all of the vectors in capital W are going to be given columns in this composition table, and the way we're going to define any element of the field scalar multiplied by any vector in W is we'll just go and have a look at the larger scalar multiplication law over here, and of course that vector, all vectors in here are up here somewhere, so all of the answers are already here, so we're just restricting down this one. We're just cutting a huge portion off basically and taking the restricted composition table. Okay, so that's what I mean by the inherited addition law and the inherited scalar multiplication law from the larger vector space. Okay, so if this subset W with this inherited addition law and this inherited scalar multiplication law actually obeys the axioms of being a vector space, i.e. this is an abelian group, and this obeys all of those axioms that scalar multiplication needs to obey, then we call W a subspace of V. Okay, and the way that this is written usually is W is less than or equal to V, so it's just like the notation for W is a subgroup of V. Now, there's a little bit of controversy around this. You will have a trouble finding a textbook actually writing this. Okay, this is the notation that everyone uses for V is a subspace of W. Sorry, V, other way around. W is a subspace of V. However, no one actually writes it in textbooks. It's kind of like the notation that everyone knows is what everyone uses, but no one has officially said that it's okay to use this. Okay, so officially I suppose there is no actual notation for saying W is a subspace of V. You have to actually write out W is a subspace of V. Okay, but this is the notation that everyone uses, and everyone will know what you mean if you put W is less than or equal to V. Okay, and it's important to point out that if W is a subspace of V, then W will be a subgroup of V. So if you think of V now just as being a subgroup, if you just think of V as being a group with the addition law on it, then W is a subset with a inherited addition law on it, which needs to be a group in its own right in order for W to be a subspace. Therefore, W can be viewed as a subgroup of V, so that's why the notation is probably so similar. Okay, so this is how we will be writing W is a subspace of V, but as I say, you won't, or at least you'll have trouble finding a textbook using this notation because it's not absolutely formal. Okay, but everyone will know what you mean if you write W is less than or equal to V. Okay, so what we're going to do in the next video then is we're going to look at 3 criteria which actually, if a subset obeys those 3 criteria, it will mean that that subset is actually a subspace of the vector space capital V. What it will then be our task to do is show how these 3 criteria being true will actually mean that all of the axioms of an abelian group are satisfied by the addition composition table restricted down here, and all of the axioms of scalar multiplication are satisfied by our scalar multiplication table restricted down in this way. Okay, so we'll do that in the next video.